General circulation of the atmosphere. The pattern of planetary winds depends on several factors. Latitudinal variation of atmospheric heating, emergence of pressure belts, the migration of belts following the apparent path of the Sun, the distribution of continents and oceans, and the rotation of the Earth. The pattern of the movement of the planetary winds is called the general circulation of the atmosphere. The general circulation of the atmosphere also sets in motion the ocean water circulation, which influences the Earth's climate. Hadley cell. The air at the Intertropical Convergence Zone, or ITCZ, rises because of the convection currents caused by low pressure. Low pressure, in turn, occurs due to high insolation. The winds from the tropics converge at this low-pressure zone. The converged air rises along with the convective cell. It reaches the top of the troposphere up to an altitude of 14 kilometers and moves towards the poles. This causes accumulation of air at about 30 degrees north and south. Part of the accumulated air sinks to the ground and forms a subtropical high. Another reason for sinking is the cooling of air when it reaches 30 degrees north and south latitudes. Down below, near the land surface, the air flows towards the equator as the easterlies. The easterlies from either side of the equator converge in the Intertropical Convergence Zone, or ITCZ. Such circulations from the surface upwards and vice versa are called cells. Such a cell in the tropics is called the Hadley cell. Feral cell. In the middle latitudes, the circulation is that of sinking cold air that comes from the poles and the rising warm air that blows from the subtropical high. At the surface, these winds are called westerlies, and the cell is known as the feral cell. Polar cell. At polar latitudes, the cold, dense air subsides near the poles and blows towards middle latitudes as the polar easterlies. This cell is called the polar cell. These three cells set the pattern for the general circulation of the atmosphere. The transfer of heat energy from lower latitudes to higher latitudes maintains the general circulation. The general circulation of the atmosphere also affects the oceans. The large-scale winds of the atmosphere initiate large and slow-moving currents of the ocean. Oceans, in turn, provide input of energy and water vapor into the air. These interactions take place rather slowly over a large part of the ocean. Walker cell. The warming and cooling of the Pacific Ocean is most important in terms of general atmospheric circulation. The warm water of the central Pacific Ocean slowly drifts towards the South American coast and replaces the cool Peruvian current. This appearance of warm water off the coast of Peru is known as the El Nino. The El Nino event is closely associated with the pressure changes in the Central Pacific and Australia. This change in pressure condition over the Pacific is known as the Southern Oscillation. The combined phenomenon of Southern Oscillation and El Nino is known as ENSO. In the years when the ENSO is strong, large-scale variations in weather occur over the world. The arid west coast of South America receives heavy rainfall. Drought occurs in Australia and sometimes in India, and floods in China. This phenomenon is closely monitored and is used for long-range forecasting in major parts of the world. We will discuss El Nino in more detail later. Classification of winds. Permanent winds, or primary winds, or prevailing winds, or planetary winds include the trade winds, westerlies and easterlies. Secondary or periodic winds include seasonal winds, which change their direction in different seasons, like the monsoons in India. Periodic winds also include land and sea breezes, as well as mountain and valley breezes. Local winds blow only during a particular period of the day or year in a small area, such as the Lu, Mistral, Fern and Bora. Primary winds or prevailing winds, or permanent winds or planetary winds, are the planetary winds that blow extensively over continents and oceans. The two most well understood and significant winds for climate and human activities are trade winds and westerly winds. Trade winds. The trade winds are those blowing from the subtropical high-pressure areas towards the equatorial low-pressure belt. Therefore, these winds are confined to a region between 30 degrees north and 30 degrees south throughout the Earth's surface. They flow as the northeastern trades in the northern hemisphere and the southeastern trades in the southern hemisphere. This deflection, in their ideally expected north-south direction, is explained on the basis of Coriolis force and Farrell's law. Trade winds are descending and stable in areas of their origin, the subtropical high-pressure belt, and as they reach the equator, they become humid and warmer after picking up moisture on their way. The trade winds from the two hemispheres meet at the equator, and due to convergence, they rise and cause heavy rainfall. The eastern parts of the trade winds, associated with the cool ocean currents, are drier and more stable than the western parts of the ocean. Westerlies. The westerlies are the winds blowing from the subtropical high-pressure belts towards the subpolar low-pressure belts. They blow from southwest to northeast in the northern hemisphere and northwest to southeast in the southern hemisphere. The westerlies of the southern hemisphere are stronger and more persistent due to the vast expanse of water, while those of the northern hemisphere are irregular because of the uneven relief of vast land masses. The westerlies are best developed between 40 and 65 degrees south latitudes. These latitudes are often called the roaring 40s, furious 50s, and shrieking 60s, dreaded terms for sailors. The poleward boundary of the westerlies is highly fluctuating. There are many seasonal and short-term fluctuations. These winds produce wet spells and variability in weather. Polar easterlies. The polar easterlies are dry, cold, prevailing winds blowing from northeast to southwest direction in the northern hemisphere and southeast to northwest in the southern hemisphere. They blow from the polar high-pressure areas to the subpolar lows. Secondary winds or periodic winds. These winds change their direction with the change in season. Monsoons are the best example of large-scale modification of the planetary wind system. Other examples of periodic winds include land and sea breeze, mountain and valley breeze, cyclones and anticyclones, and air masses. Monsoons were traditionally explained as land and sea breezes on a large scale. Thus, they were considered a convectional circulation on a giant scale. The monsoons are characterized by seasonal reversal of wind direction. During summer, the trade winds of the southern hemisphere are pulled northwards by an apparent northward movement of the sun and by an intense low-pressure core in the northwest of the Indian subcontinent. While crossing the equator, these winds get deflected to their right under the effect of the Coriolis force. These winds now approach the Asian landmass as southwest monsoons. Since they travel a long distance over a vast expanse of water, by the time they reach the southwestern coast of India, they are oversaturated with moisture and cause heavy rainfall in India and neighbouring countries. During winter, these conditions are reversed, and a high-pressure core is created to the north of the Indian subcontinent. Divergent winds are produced by this anticyclonic movement which travels southwards towards the equator. This movement is enhanced by the apparent southward movement of the sun. These are northeast or winter monsoons, which are responsible for some precipitation along the east coast of India. The monsoon winds flow over India, Pakistan, Bangladesh, Myanmar, Burma, Sri Lanka, the Arabian Sea, Bay of Bengal, Southeastern Asia, Northern Australia, and China. Outside India, in the Eastern Asiatic countries such as China and Japan, the winter monsoon is stronger than the summer monsoon. We will study monsoons in detail while studying the Indian climate. Monsoons are periodic winds. The land and sea absorb and transfer heat differently. During the day, the land heats up faster and becomes warmer than the sea. Therefore, over the land, the air rises, giving rise to a low-pressure area, whereas the sea is relatively cool, and the pressure over the sea is relatively high. Thus, a pressure gradient from sea to land is created, and the wind blows from the sea to the land as the sea breeze. At night, the reversal of conditions takes place. The land loses heat faster and is cooler than the sea. The pressure gradient is from the land to the sea, and hence a land breeze results, land and sea breeze. In mountainous regions during the day, the slopes get heated up and air moves upslope. To fill the resulting gap, the air from the valley blows up the valley. This wind is known as the valley breeze. During the night, the slopes get cooled and the dense air descends into the valley as the mountain wind. The cool air from the high plateaus and ice fields draining into the valley is called katabatic wind. Another type of warm wind, also a katabatic wind, occurs on the leeward side of the mountain ranges. The moisture in these winds, while crossing the mountain ranges, condenses and precipitates. When it descends down the leeward side of the slope, the dry air gets warmed up by the adiabatic process. This dry air may melt the snow in a short time. Valley breeze and mountain breeze. Tertiary winds or local winds. Local differences of temperature and pressure produce local winds. Such winds are local in extent and are confined to the lowest levels of the troposphere. Some examples of local winds are discussed below. Local winds: Mistral, Sirocco, Fern. In the plains of northern India and Pakistan, sometimes a very hot and dry wind blows from the west in the months of May and June, usually in the afternoons. It is known as Lu. Its temperature invariably ranges between 45 degrees Celsius and 50 degrees Celsius. It may cause sunstroke to people. Fern or Phone. Beneficial wind. Fern is a hot wind of local importance in the Alps. It is a strong, gusty, dry and warm wind which develops on the leeward side of a mountain range. As the windward side takes away whatever moisture there is in the incoming wind in the form of orographic precipitation. The air that descends on the leeward side is dry and warm, known as a katabatic wind. The temperature of the wind varies between 15 degrees Celsius and 20 degrees Celsius. The wind helps animal grazing by melting snow and aids the ripening of grapes. Chinuk, beneficial wind. Fern-like winds in the USA and Canada move down the west slopes of the Rockies and are known as Chinuk. It is beneficial to ranchers east of the Rockies as it keeps the grasslands clear of snow during much of the winter. Mistral, harmful wind. Mistral is one of the local names given to such winds that blow from the Alps over France towards the Mediterranean Sea. It is channeled through the Rhine Valley. It is very cold and dry with a high speed. It brings blizzards into southern France. Sirocco, harmful wind. Sirocco is a Mediterranean wind that comes from the Sahara and reaches hurricane speeds in North Africa and southern Europe. It arises from a warm, dry tropical air mass that is pulled northward by low-pressure cells moving eastward across the Mediterranean Sea, with the wind originating in the Arabian or Sahara deserts. The hotter, drier continental air mixes with the cooler, wetter air of the maritime cyclone, and the counterclockwise circulation of the low propels the mixed air across the southern coasts of Europe. The Sirocco causes dusty, dry conditions along the northern coast of Africa, storms in the Mediterranean Sea, and cool, wet weather in Europe.